Right. So I've had a few requests for help with mechanisms. Obviously, you've got plenty of them in your books already. But some of the questions about mechanisms, rather than what is the mechanism, it's why does it go like that? So for what it's worth, I thought, well, I'll put a few little videos together so you can just pick and use them as you need. Some of these are so simple, I don't think you'll really need to be revising it, but better safe than sorry. So first of all, nucleophilic substitution. You know how simple it is. The first arrow is always from the lone pair on a nucleophile, hydroxide, cyanide or ammonia, or an amine. It could be NR3 instead, yeah, to that carbon there. We'll think about why that carbon in a quick second. And ultimately, the consequence of bonding to that carbon is that something has to leave. There's a good leaving group here. That idea of a leaving group crops up on the next page as well when we look at the addition reactions, nucleophilic addition types. You'll see. But anyway, there it is. So for the first two there, that's all there is to it. Again, you probably don't need to be revising this, but it doesn't hurt to be thorough. So you can have a go at naming those molecules as well. Remember that for the ammonia reaction there's like a second step because you get an intermediate rather than the final product. So we get an NH3 plus group. Remember, if you see a nitrogen with 4 bonds, it just does have a plus on it. Just stick it on and don't overthink why. And then one of these nitrogen-hydrogen bonds has to break. We don't actually need to show what takes it, though there is a bit of a discussion about that with further substitution of haloalkanes. That's what we get. And so there we are. Really quick opportunity, take it while it's there, to name these products. So I'll come back to the side products there as well. This is easy, it's just propan-2-ol. This is a nitrile. Remember the rules for naming nitriles. The nitrile carbon has to be carbon 1. So it's obviously a branch chain either way. Doesn't matter if you number to the left or the right, those methyl groups. So you've got a propane nitrile. I'll write this one down. And there's a methyl group on carbon 2. We don't really need to stipulate that it's on carbon 2 because if it were anywhere else that would have changed the name. It's methyl propane nitrile. Put it on carbon 3, we'd have had butane nitrile instead. Can't go on carbon 1 because there's no room for it. Name of this amine here, well, in loose terms it's propylamine, except then we need to be clear whether it's on carbon 1 or 2. If the NH2 had been on carbon 1, so it was like a straight chain, that would be propylamine. This isn't, obviously it's a branch, so we can call it 2-propyl amine or prop-2-ol amine. I don't think we really need to worry about naming these, to be honest with you, as much as drawing the structure. Without waffling too much, the point is that this amine product is also a nucleophile. It's just like ammonia, it's got a lone pair on the end. It's actually a stronger nucleophile than ammonia was because of the inductive effect. This alkyl group here, this carbon in particular, is having electron density pulled away from it by that more electronegative nitrogen atom, which kind of increases the availability of the lone pair to react. So if we had an excess of haloalkane, this could go again, where instead of NH3, we've got RNH2, where R is this prop-2-ol group. I'm not going to go through the whole mechanism again, but further subs is possible. A second haloalkane molecule comes along. There's the nitrogen that was once part of an ammonia. And in the second substitution step, we go to having something like that. Okay? And then again, if there was still an excess of haloalkane, a third substitution could take place. We'll end up with 3 of these branched propyl groups. And it's still got a lone pair, which is now even more available because it's triply boosted by the inductive effect on all fronts. And that can go one final step, at which point it terminates the sort of process. Be careful with that word termination, because this isn't free radicals, and that's where the word termination normally comes in. We'd end up with this tetra-substituted ammonium salt. And if we had to draw the structure of that or name it, well, we're not going to have to name this one here. If there were straight chains, it would be like tetrapropyl ammonium. Obviously, it's not an amine anymore, it's an ammonium salt. And if this was a bromoalkane, there'd be a bromide ion to balance its charge. So just like NaCl, obviously we call it sodium chloride, this is tetrapropyl ammonium bromide. Don't forget the anion. And that's the further subs. Obviously, that's if you've got an excess of haloalkane. Okay, you can't stop or prevent further subs from happening, but you can influence that it shouldn't happen as much as otherwise by using an excess of the nitrogen-bearing molecule if it's ammonia or an amine that you're starting with. Okay, on we go. Now, the one thing to say here, and really this is setting us up for a similar narrative on the next page, is why does that happen in the first step? Well, because we say this bond is polarised, and that comes down to a difference in electronegativity. If you actually look at the electronegativity values, there's very little difference between carbon and bromine. I don't think it really is because of that. It's just what the textbooks say. But that is what the textbooks say. We'll play the game. Carbon and iodine are basically the same in terms of electronegativity. There is another factor at play. It's to do with the relative strength of the bond. As these bonds get longer, obviously as the atoms get bigger, the bonds have to get longer. They get weaker. And on top of that, as well as the Y does the nucleophile bond to that C there, well, because it's delta plus is basically what we're saying. It's also the case of, there's a good leaving group, a halide ion, which is, they're very common. We see examples of them all the time. So nature must love it. So it's not weird and exotic and forbidden by nature, quite the opposite. Anyway, right, now let's take this and run with it. The question that somebody was asking was just trying to clarify when it's addition and when it's addition-elimination. From a sort of just learning the facts point of view, I'd say, well, it depends on which functional groups you've got. But I will look at it in a slightly more scientific way by talking about leaving groups again. So the nucleophiles for nucleophilic addition are hydride and cyanide. Those are the only two on the list. Obviously some exam question might give us an unfamiliar example where they tell us that, I don't know, like methanol or something like that acts as a nucleophile, in which case we can apply what we know to that example. It's got a lone pair on it somewhere, but these are the two which are actually specified. So one way of looking at how do I know if it's nucleophilic addition or something else is, well, if you're starting with an aldehyde or a ketone and it's reacting with hydride or cyanide, then it is, else it isn't, okay? From a practical point of view though, we should just be aware that source of hydride ions is NaBH4. We definitely don't want to be trying to use the borohydride anion in the mechanism. Just use hydride. Obviously and famously our source of cyanide is typically potassium cyanide. It's a soluble ionic. You can actually use HCN, which is a weak acid, and it's a simple molecule. It's not ionic, so it doesn't actually contain cyanide ions. It's extremely weak. It's Kas of the order of like 10 to the minus 10. It can be used on OCRA level. That's what we're supposed to talk about. Not for us, so be aware in case you see that, but we'll assume it's an ionic cyanide, so it's KCN. Anyway, I'll only do this one once. It could go from either. I'll do with the cyanide. Arrow from the lone pair on the nucleophile, causing the double bond to open up. Now we're going to see those same two opening moves when we look at acyl chlorides in a second. What happens next is where nucleophilic addition and addition-elimination diverge though. Well, I'll say what happens next. We get this intermediate as well. So the carbonyls opened up, so we've got lone pair on the O minus. The nucleophile, I've chosen to work with CN as bonded. If it's CN, it has to be bonded through its C, because that's the lone pair that reacts. We get this intermediate. Now, unlike what we'll be saying for the next one, addition-elimination, there's no good leaving group on that intermediate. There's no halide that could be kicked out as a chloride ion, etc. And so instead of that, the best option is the solvent. If it's acidified aqueous solution or if it's just water, okay, non-acidified, either way there's a source of H plus ions there somewhere. And so the lone pair on that single bondo doesn't go to reform the carbonyl, which is what happens on the next mechanism, but rather just simply bonds to a H from somewhere. And that somewhere, it could be a H2O molecule that has a H plucked off it, it could be acidified, it could be HCl solution, in which case there's a load of H3O plus floating around. Either way, we get the carbonyl being reduced down to an alcohol and a new group added on. So that's obviously nucleophilic addition, something gets added together. Now, our definition for a nucleophile is obviously an electron pair donor, and they are always attracted to and so donate that pair of electrons to something electron deficient. So these three mechanisms I'm running through in this video, they all start with nucleophilic in their title. They all involve, well, an electron pair donor bonding to something. That's pretty much always true. But you can see here in each case, we've had the haloalkane one, now we've got a carbonyl example. There's a delta plus carbon to which something bonds or coordinates really, that we don't call these ligands because there's not a metal centre there, okay? That could be an aldehyde or a ketone, so in other words that could be butanone as I've got there, or I could just put a H on and now it's actually propanal. Either way, it's an aldehyde or a ketone. Now, nucleophilic addition-elimination, I'm only going to do 2 of the possible 4 options. Just as a quick reminder, nucleophile bonds to that carbon because it's delta plus, okay? Causing the carbonyl to open up, and then something about leaving groups. I said there isn't one here, so the OH gets put in the place of the carbonyl. And that requires a proton donor, if it's just water or if it's acidified. Here there is a good leaving group, it's that Cl. So first of all, the same thing. I'm just going to use water or ammonia in these two examples. That could be an alcohol, it could be ROH instead of HOH. This could be an amine, it could be RNH2 instead of NH3, you know, but I'm just picking two of them. Either way, the same thing happens in that the nucleophile bonds to the carbonyl. Same in both these because this is one mechanism, also the same as what we've had up there in nucleophilic addition. Those two opening moves or opening steps are the same, okay, across the two nucleophilic addition type mechanisms. This intermediate is also the same as what we had above in that the carbonyls now become single bond O minus with a lone pair. The point is there's a Cl on that carbonyl carbon as well. Something has just attached. In this case it was a water molecule, and in this one here it's an ammonia molecule, both of which have now gained a positive charge, and that would be true if this was ROH and RNH2. You can see it'd just be switching out a H for an alkyl group of some sort. They've both got more bonds than they would typically have in a neutral molecule. They're all 1+, okay? Whenever an atom bonds coordinately to something, it always gains a positive charge, okay? What we had in nucleophilic addition was an anion becoming neutral, so Cn- becomes Cn. Here we've got something neutral going up to 1+, OH2 becomes OH2+, and so forth. Right, this time there is a good leaving group, so we don't need H+ to come along. Instead of that, the carbonyl reforms, kicking off the Cl to make space for it. That happens, I'm just going to do both mechanisms in parallel here, either way. And then whatever this group is down here, basically the remnants of the nucleophile, which has gained a positive charge on the atom it bonded through, that thing there needs to lose a H. So OH2 becomes OH by losing a H, NH3+, the same. Notice the direction of the arrows. People always get these arrows wrong for some reason. The arrows have to go to the thing that's to the atom which is positively charged. That neutralizes the charge. It means this bonding pair here becomes a lone pair, and this H is taken away by something that we don't need to draw. It could be a chloride ion that's been freed up from another molecule. So I'll just try and find a bit of space to draw the structure of the products in case that helps. So here we get here we get a carboxylic acid and hydrogen chloride gas. Here we get an amide. Again, for some reason amides cause confusion. It's just a carboxylic acid with NH2, whoops, gone off the screen, instead of OH, and again hydrogen chloride. So there it is. So to answer the question of why do these reactions happen the way they do, well, it all kicks off with a delta plus carbon, either a C halo bond or a carbonyl having some electron-rich species, a nucleophile, one of the ones we've drawn here, bonding to it. Now, H2O, or ammonia, or an alcohol, or an amine, i.e. the nucleophilic addition-elimination nucleophiles, they can't react with aldehydes or ketones. So just in case this helps, a question of, well, why is that then? Well, they're just not strong enough nucleophiles, basically. Yeah, we know that, you know, there are lots of chemicals out there that have lone pairs on them, but it's all about the relative availability of them, something we don't really need to worry about even as A-level chemists. So something like an ammonia molecule or a water molecule, yeah, they have lone pairs, but they're just not attracted strongly enough to this carbonyl carbon here in an aldehyde or a ketone. It is definitely a polarized bond. O is definitely quite a lot more electronegative than carbon, but it's not as delta plus as, say, here, where you've got a carbon which is bonded to a Cl and an O. So two of the most electronegative elements bonded to that same carbon. So that's a really significant delta plus, okay? Which is why even water, which is a pretty measly nucleophile, can do that, okay? So there's the question of why, and I'm saying you don't really need to know, but we've had a look at it anyway. There's a question of how. Well, there's the pattern of the mechanism, and there we are, okay? I'll do a similar one for the electrophilic reactions, and then the one for the ones that are acid catalyzed or start with a H being taken off something. Hopefully that helps.